or when we dip the chalk piece or a activated charcoal in the. Now let us start with a new topic, surface chemistry. This topic deals with the study of reactions occurring at the surface or at the interface of phases. To understand such reactions, it is necessary to understand the meaning of this term adsorption. Now, what this adsorption is? See, when we expose the metal surface to a gas, then the molecules of a gas, they get collected onto the surface of a metal. Or when we dip the chalk piece or a activated charcoal in the liquid, the molecules of a liquid, they get collected onto the surface of that chalk piece or activated charcoal. See, this phenomenon of accumulation of a gas or liquid molecules onto the surface of a solid is known as adsorption. Adsorption is a surface phenomenon because in an adsorption the molecules of a gas or a liquid, they get collected only onto the surface of a solid. One more like sounding term is there, that is known as a absorption. In absorption, the molecules of a liquid, they penetrate deep into the body of a solid and get uniformly distributed. So therefore, that solid becomes wet from inside as well as from outside. This phenomenon is known as absorption. Now, some important terms of this topic. In that, the first one is the adsorbent. The surface of a solid where molecules of a gas or a liquid adsorb is known as a adsorbent. Adsorbents are of two types. One is porous adsorbents. For example, activated charcoal, which we had taken here in this example. Silica gel, silica, alumina, etc. As far as the metal adsorbents is concerned, in that the metals like zinc, nickel, gold, aluminium, platinum, etc. These are the examples of metal adsorbent. One more term which is quite important, that is adsorbate. The gas or a liquid which gets adsorbed onto the surface of a solid adsorbent is known as a adsorbate. Adsorbate may be a gas or liquid. In this example, these gas molecules which got adsorbed onto the surface of a solid activated charcoal are the adsorbate. One more example, say in the adsorption of a hydrogen onto the surface of a nickel, hydrogen act as an adsorbate whereas nickel act as an adsorbent. Now then, what's the meaning of this term desorption? The process of removal of adsorbed substance from the surface of a adsorbent is called desorption. The process of removal of adsorbed substance from the surface of a adsorbent is called desorption. This desorption is opposite to that of a adsorption process. Now then, the next term is heat of adsorption. This phenomenon of adsorption is the exothermic process. So therefore, during the adsorption of a gas or a liquid molecules onto the surface of a adsorbent, some amount of a heat energy is liberated or evolved. See then, the amount of a heat evolved per mole of a adsorbate adsorbed is called as the heat of a adsorption or molar heat of a adsorption. Now then, the next term is adsorption isotherm. What's the exact meaning of this term? Let us try to understand. The relation between the amount of a gas adsorbed per unit mass of a adsorbent and the equilibrium pressure of a gas at a constant of temperature is represented graphically by a curve known as adsorption isotherm. You can draw the adsorption isotherm by using these two values, that is amount of a gas adsorbed per unit mass of a adsorbent and the equilibrium pressure at a constant of temperature. Such a curve is known as a adsorption isotherm. There are two types of adsorptions. One is physical adsorption and another one is chemical adsorption. Now what this physical adsorption is? In physical adsorption, physical forces or van der Waals forces of a solid hold the gas molecules at the surface. It is also known as a physisorption or van der Waals adsorption. The example is adsorption of a acetic acid onto the surface of charcoal. In physical adsorption, as we go on increasing the pressure of a gas or the surface of a adsorbent, with that one by one multiple layers are formed. On the other hand, instead of increasing the pressure of a gas, if you lower down the pressure of a gas onto the surface of a adsorbent, with that one by one the adsorbed layer gets removed from the surface of a adsorbent. That's why we call this physical adsorption as a reversible process. Now then, the next type of adsorption is chemical adsorption. In chemical adsorption, a chemical bond is formed between the solid surface and the approaching molecule. This adsorption is also known as a chemisorption because of the formation of chemical bond between the adsorbent and the gas molecule. The specific example of this kind of adsorption is the adsorption of a hydrogen gas onto the surface of nickel. Now then, what's the exact difference between physical adsorption and the chemical adsorption? Let us think over that. Now, first of all, physical adsorption. In a physical adsorption, the molecules of a adsorbent, they are held onto the adsorbent due to the weak van der Waals forces. Whereas in a chemical adsorption, the adsorbate molecules held onto the surface of a adsorbent by the formation of a chemical bond. In between adsorbate and adsorbent, here there forms a chemical bond. Now then, in a physical adsorption, see here, physical adsorption is a reversible process, whereas chemical adsorption is a irreversible process. Now, why we call this physical adsorption as a reversible process? Let us try to understand this. As I said just now, if we increase the pressure of a gas over the surface of a adsorbent, with that, one by one, a multiple layer of a gas molecules forms onto the surface of a adsorbent. Instead of increasing the pressure, if I keep on lowering the pressure of a gas over the surface of a adsorbent, then one by one the adsorbed layer gets removed from the surface of a adsorbent. That's why we call this physical adsorption as a reversible process. On the other hand, chemical adsorption is irreversible because once the monolayer or unilayer of a molecule is formed onto the surface of a adsorbent by the chemical bond, then by the chemical bond between the adsorbent and the gas molecules, then by changing the pressure of a gas, it is not possible to remove that layer from the surface of a adsorbent. That's why we call this chemical adsorption as an irreversible process. Now then, the next distinguishing character. Physical adsorption is not very specific, but the chemical adsorption is specific. Now then, in a physical adsorption, just now we had seen here a multiple layers or multi-layers of adsorbate are formed over the surface of an adsorbent. Whereas in a chemical adsorption, there forms only a unilayer or a monolayer of an adsorbent. Then the next distinguishing character is the heat of adsorption is low, that is less than 40 kilojoule per mole during the physical adsorption. You know, I already told you the meaning of this term, heat of adsorption. That is the amount of a heat evolved during the adsorption of 1 mole of a adsorbate onto the surface of a adsorbent. That is heat of adsorption, which is low in case of physical adsorption. In a chemical adsorption, see here, the heat of adsorption is high, that is between 40 to 400 kilojoule per mole. The next distinguishing character is that physical adsorption occurs at a low temperature and high pressure, whereas chemical adsorption occurs at a high temperature and low pressure. Then the last distinguishing character between these two types of adsorption is that the activation energy for physical adsorption is low, whereas activation energy for chemical adsorption is high. So like this, we are going to distinguish the physical adsorption and then the chemical adsorption. Now then, the next article is types of adsorption isotherms. We already have discussed the meaning of this term adsorption isotherm. Now let me repeat the same once again. The relation between the amount of gas adsorbed by an adsorbent and the equilibrium pressure at constant of temperature is represented graphically by a curve known as adsorption isotherm. The scientist Brunauer studied several adsorption systems and classified the isotherms into 5 types. Let us discuss one by one in detail. Type first. This type of a curve is known as Langmuir type of isotherm. It shows that with increase in a pressure, the quantity of gas adsorbed increases rapidly up to the formation of monolayer onto the surface of a adsorbent. After the first layer, adsorption rate diminishes. Diminishes means decreases, and a saturation state is reached. This type of isotherm is observed in case of chemisorption. Chemisorption means chemical adsorption. The example of this kind of adsorption isotherm is adsorption of nitrogen gas onto the surface of a charcoal at 78 Kelvin. Now let us discuss the second type of adsorption isotherm. This type of a curve is known as sigmoid type, of a isotherm. It shows that with increase in a pressure, quantity of a gas adsorbed increases till there forms a monolayer onto the surface of adsorbent, that is shown by the transition point B. Transition point B. The volume of a gas corresponds to point B is Vm. Vm, that is nothing but the volume of a gas required to cover the entire surface of a adsorbent with unimolecular thick layer. At high pressure, adsorption begins and a multimolecular layers are formed onto the surface of a adsorbent. The example of this kind of adsorption system is adsorption of a nitrogen gas onto the surface of a silica at 77 Kelvin. Now then, the next type of adsorption isotherm is type 3. This type of a curve is known as a hyperbolic type isotherm. It shows that with increase in a pressure, quantity of a gas adsorbed increases gradually and multimolecular adsorption begins before the complete formation of monolayer. The well-known example of this kind of a system is adsorption of bromine onto the surface of a silica gel at 352 Kelvin. Now the next type of isotherm is shown in the diagram. This type of a curve is known as a extended S type of isotherm. It shows that with increase in a pressure, quantity of a gas adsorbed increases till there forms a multi-molecular layer onto the surface of a adsorbent. In this case, the adsorbed gas gets condensed and sinks into the pores of a adsorbent. The example of this kind of a system is adsorption of a benzene onto the surface of ferric oxide at 323 Kelvin. Now then, the last adsorption isotherm is type 5th isotherm. It shows that with increase in a pressure, gradually gas gets adsorbed onto the surface of a adsorbent and forms a multimolecular layer. At high pressure, saturation state is reached. The example of this kind of a system is adsorption of water vapors onto the surface of a charcoal at a temperature of 373 Kelvin. Now let us discuss Langmuir adsorption isotherm. This is one of the important article of this topic. Now what this Langmuir adsorption isotherm is, let us see that. To overcome the limitations of Freundlich's adsorption isotherm, Langmuir suggested the theory for adsorption of a gas onto the surface of a solid. This theory is also known as Langmuir's unimolecular adsorption isotherm. This theory is based on the following assumptions. The first assumption of this theory is that all the gases under study behaves like ideal gas. The second assumption is that the adsorbed layer of a gas molecule onto the surface of an adsorbent is unimolecular in thickness. The next assumption is that the amount of a gas adsorbed on the surface of an adsorbent depends upon the surface area of the adsorbent. Larger is the surface area with the adsorbent, larger will be the amount of a gas that get adsorbed on its surface. The next assumption is that the rate of adsorption is proportional to the pressure of the gas over the surface of a adsorbent. Now the next assumption is the rate of adsorption is proportional to the uncovered surface area of the adsorbent. Larger is the uncovered surface area with the adsorbent, the rate of larger will be or higher will be the rate of adsorption. The next assumption is that the rate of desorption is proportional to the surface area of adsorbent covered by the gas molecule. Now then, the next assumption is very important. Assumption is adsorption is a dynamic process. It consists of two opposite actions. One is adsorption of a gas molecules on the surface of a solid, desorption of a gas molecules from the surface of a solid. And the rate of adsorption becomes equal to the rate of desorption. Then the process attains equilibrium, which is called adsorption equilibrium. On the basis of these assumptions, Langmuir derived an equation called Langmuir adsorption isotherm. Now consider the unit surface area of the adsorbent. Unit surface area, that is nothing but say 1 square centimeter or 1 square meter, like that. Let theta be the fraction of the surface covered by the gas molecule. Theta be the fraction of the surface covered by the gas molecules. Then the fraction of uncovered surface area will be 1 minus theta. Now then, according to the assumptions, the rate of adsorption is proportional to the uncovered surface area of the adsorbent as well as the pressure of a gas, which can be written as K1 1 minus theta into P. Here this K1 is the proportionality constant. Now the rate of desorption is proportional to the surface area of the adsorbent covered by the gas molecules, which can be written as K2 into theta, where K2 is the proportionality constant. In the state of equilibrium, rate of adsorption is equal to rate of desorption. Let us substitute the values of rate of adsorption and rate of desorption. So K1 into bracket 1 minus theta into P is equal to K2 theta. Let us simplify this equation. K1 into 1 into P, that is K1P, minus K1 theta P, which is equal to K2 theta. Transfer this negative quantity to the opposite side. At the opposite side, it becomes positive. Now then, let us take out this theta as a common. We will get this equation. Then theta is equal to K1P divided by K2 plus K1P. Like this, we can write the equation. Now dividing numerator and denominator by K2. After then, we will get this equation in this form. So therefore, theta is equal to B into P divided by 1 plus B into P, where B is equal to K1 upon K2, which is nothing but the adsorption coefficient. And we can cancel K2 and K2. The amount of gas adsorbed per unit mass of a adsorbent, that is Y, is proportional to the covered surface area of adsorbent, that is theta. So therefore y is proportional to theta. We can remove this proportionality sign by the constant known as proportionality constant. Let us substitute the value of a theta from equation number 1. So we'll get y is equal to k b into p divided by 1 plus b into p. Now we can write this equation as y is equal to a into p divided by 1 plus b into p, where a is another constant which is equal to k into b. This equation number 2 is known as a Langmuir adsorption isotherm. Now testing the validity of Langmuir adsorption isotherm. To test the Langmuir adsorption isotherm for the given system, we need to rearrange the equation number 2. Now transfer this denominator quantity to the opposite side. I did it here, which is equal to a into p. After then, transfer this y to the opposite side and this a to the opposite side. You will get this equation in this form. This equation is of the type y is equal to mx plus c. This is an equation of that straight line which is having an intercept on a y-axis. By using the experimental values of p upon y on a y-axis and the pressure values on a x-axis, when we plot a graph, we will get such a straight line plot. The slope of this straight line will be b upon a, whereas the intercept made by this straight line on a y-axis will be equal to 1 upon a. Thus, Langmuir adsorption isotherm equation is verified because we got a linear plot as per the expectation of this equation. Now we need to write this much if the question is asked on this Langmuir adsorption isotherm. Now our next article is BAT adsorption isotherm. This is again another important article of this topic. We had seen the Langmuir theory of unimolecular adsorption is valid only at comparatively low pressure and high temperature. But as the pressure is increased and temperature is lowered, additional layers are formed onto the surface of first monolayer. The concept of multilayer adsorption was studied by Brunauer, Emmett and Taylor and derived an equation known as BET equation or isotherm. BET isotherm is based on the following postulates. The first postulate of this BET isotherm is the adsorbed layer may be multimolecular in thickness. The second postulate is that Langmuir's assumptions apply to each layer present in the adsorption system. The next assumption is that there is a dynamic equilibrium between the successive layers. The rate of evaporation from one layer is equal to the rate of condensation on the preceding layer. The next postulate is that the characteristic heat of adsorption is applicable to only the first layer which forms onto the surface of adsorbent. After the first layer, the heat of adsorption is equal to the heat of condensation of vapor. The next postulate is that the derivation is based on the same kinetic picture as represented by Langmuir. The condensation forces are the principal forces in adsorption. These are the postulates of PET isotherm. On the basis of above postulates, BET derived an equation known as BET isotherm. In this equation, this P denotes the pressure at a temperature T. V denotes the volume of a gas adsorbed per unit mass of a adsorbent at a pressure P and the temperature T again. P0 denotes the saturated vapor pressure at the same temperature. Vm, that is nothing but volume of the gas required to cover unit mass of a adsorbent with a single layer, and this C is a constant for a given adsorbent and is given by the equation C is equal to exponential raised to delta H1 minus delta Hm upon RT. R is the gas constant, T is the temperature in Kelvin, whereas delta H1 is the heat of adsorption of the first layer which directly forms onto the surface of a adsorbent. Delta Hm is the heat of adsorption of all layers formed above the first layer. Now, the next point in this topic is, in question paper, the question may be of this kind: write BET equation and explain the terms involved in it. And secondly, how is the equation verified? Like this, you may find the question in the question paper. Now, how to write the answer of this question? This concept of multilayer adsorption was studied by Brunauer, Emmett, and Tiller, and derived an equation known as BET equation or isotherm. We need to write this BET equation as it is, and after then we need to write the meaning of each term involved in this equation. Just now I told you the meaning of these all terms. Then, how is the equation verified? The BET equation is verified by plotting a graph of P upon V into bracket P0 minus P, means this first term, against P upon P0, this term. The graph is linear with a slope C minus 1 upon Vm into C and intercept 1 upon Vm into C. To plot this graph experimentally, we need to obtain the values of this ratio P upon V, P0 minus P at different values of a pressure P upon P0. And after then, we need to plot this graph. The linear plot indicate that the BET isotherm is valid for the given adsorption system. Instead of getting us like this linear plot, if we would have got the non-linear plot or a curve, then we would have said that the BET isotherm is not valid for the given adsorption system. So like this, we need to write the answer of this question if the question is asked in the question paper. Now then, the application of BET equation. The BET equation is used to determine the surface area of an adsorbent. Consider the adsorption of a nitrogen gas onto the surface of silica gel at a temperature of 77 Kelvin. The surface area of a silica gel is determined as follows. A graph of P upon V, P0 minus P against P upon P0 is plotted by using the experimentally obtained values. From the slope and intercept of a linear plot, the volume Vm is calculated. You know that Vm, that is nothing but the volume of a gas required to form or to cover a unimolecular thick layer onto the surface of adsorbent. So Vm can be calculated like this. The slope plus intercept is equal to slope, that is C minus 1 upon Vm into C, plus intercept 1 upon Vm into C is equal to, we can simplify this, C minus 1 plus 1. So like this we can write the numerator quantity and denominator quantity is same. So therefore Vm into C, which is equal to C upon Vm into C, because minus 1 plus 1 it becomes 0. So C upon Vm into C, you will get the equation like this. We can cancel out C and C, one from numerator and one from denominator, and you will get the equation like this, 1 upon Vm. Slope plus intercept is equal to 1 upon Vm. Or we can rearrange this equation, Vm is equal to 1 upon slope plus intercept. By substituting the values of slope and intercept in this equation, we can calculate the value of a Vm. Now then, the value Vm is reduced to standard temperature and pressure, STP, and number of moles of gas adsorbed is calculated by using the equation, that is P0 Vm is equal to N R T0, or N, that is nothing but number of moles of a gas adsorbed, N is equal to P0 Vm upon RT0. Now then, the number of molecules of a gas adsorbed can be calculated by using this equation. X is equal to N, that is nothing but number of moles of a gas adsorbed onto the surface of adsorbent, into the Avogadro's number. We know that 1 mole of any gas containing Avogadro's number of a molecule. That's why Avogadro's number is used here to calculate the number of molecules present in n moles of a gas. Now then, substituting the value of a n in this equation. So you will get x is equal to n, that is nothing but P0 Vm upon RT0 into Avogadro's number. If A is the area occupied by each adsorbed molecule, then the total surface area S of the adsorbent is given by an equation, that is S is equal to X into A. A is the area occupied by each adsorbed molecule, and X, that is nothing but the number of molecules of a gas adsorbed onto the surface of a adsorbent. Now let us substitute the value of a x from the above equation. So you will get the equation in this form: S is equal to P0 Vm upon RT0 multiplied by N into A. Here S, that is nothing but the surface area of the adsorbent. By using this equation, you can calculate the surface area of any adsorbent.